Okay, so I took it upon myself here to do problem number 13 from section 2.6. Seemed pretty fun, so I did it. They give you a function of x and y. I call it psi of x and y, and it's this, the integral from x0 to x of m of s comma y0 ds plus the integral from y0 to y of n of x comma t dy. Okay, and we know they tell us in the problem that m and n satisfy the differential equation thing to make it exact. So they tell us essentially that the partial of m with respect to y is equal to the partial of n with respect to x. And they want to show that this function satisfies it is a solution to the differential equation. I got the differential equation down at the bottom. This equation right here, this is our standard first order differential equation that we're checking to see if it's exact. So we're saying we have a solution, and so the solution would take the form of, where am I? Right. Would take the form of psi of xy equals a constant. Right. And so to check to see if this function, right, we don't have to come up with this function. They give it to us. We just have to check to see that it is a solution to the differential equation. So we need to look at psi of xy equals a constant and implicitly differentiate, right? We look at this psi of xy equals a constant, and we want to implicitly differentiate to get this. And the hope is that this will be the m plus n dy dx equals 0, which would show that this is this is indeed a solution to the differential equation given. Right? This implicit differentiation is going to give us this. It's the question is, does this match what we started with before, with an m here and an n there? So there's two partial derivatives I need to do. I need to do the partial of psi with respect to x and the partial of psi with respect to y, and I'll do them separately. So psi is this big old function here. So taking the partial with respect to x is just saying take the partial of this whole thing with respect to x. Now, it's a sum of two things, so I'm going to take the partial derivative of each of those integrals. So it looks like this. The first integral is simply the fundamental theorem of calculus. This is an integral with respect to integral with respect to x, and the x is used in the upper endpoint of that integral. So the fundamental theorem of calculus part 1 tells us just take the x and plug it in for the dummy variable, and that's what I did. I just plugged the x in for the m there. So if I integrate and then take the derivative, I get this. Now I still have to do the derivative of this part. Well, this is an integral with y's here, but the derivative with respect to x. So you're integrating with respect to, that's not supposed to be a y, that's supposed to be a t. There we go, now it's a t, and also notice it's a t up here and a t up there like it should have been. So that's the dummy variable. You're integrating with respect here. It's playing the role of y here, but we want y to be the upper limit of the endpoints, the upper limit of the interval, so you use the dummy variable in that spot. So we're integrating with respect to y, but we're differentiating with respect to x. So the thing is, you can do that in either order that you want. So what I do from here to here is just I switch the order of the integral and the derivative. So now I have the partial of n with respect to x. But I know from above that the partial of n with respect to x is equal to the partial of m with respect to y. So I'm going to replace this here, this nxt partial with respect to x, by mxt partial with respect to y, because those are equal to each other. But now I'm back to a fundamental theorem of calculus again, where the partial of, if I take the partial derivative of this thing with respect to y, and then I integrate it with respect to y, I would just get the y's plugged in here. I take the derivative, take the integral, get back to where you started from, maybe with a plus c, but the plus c will go away when you do the subtraction of those two things. So anyway, this is just m xt evaluated between y and y0, so you plug the y in for t, you plug the y0 in for t, and then this thing, the minus that, is the same as what we had from before, and it cancels out, and that's just m. The short on that is that the partial of phi with respect to x is m. Okay, now I want to do the partial of phi with respect to y. Partial of phi with respect to y, this one goes a little quicker than the other one. It's the partial with respect to y. I've already said, well, then it distributes over that plus sign, so take the partial of both of these things. But this one right here is just a 0 because there's no y's in it. That's a y sub 0. That's a constant. The s is sitting in the place of the x. The only variable there is the x, and it's not y, so the partial with respect to y is 0. Now over here, this is fundamental theorem of calculus. So the integral of the derivative of the integral, just plug that upper endpoint in for the dummy variable t, and I get n of xy. So the partial with respect to y is just n. So this equation, which we got from implicitly differentiating we start with the equation phi of xy equals a constant. We implicitly differentiate to get this, but this is equal to m, and that is equal to n. And so we end up with the equation that we started with. So phi is, in fact, a solution to this differential equation right here. Wow, that was fun.